Hi, good morning everyone, and thanks for joining today in this session. I will be talking about the paper that I wrote together with my colleagues Simon, Matthieu, Mehrzad, and the name is named Structuring Knowledge for AI-Driven Schedule Management in Digital Construction Tools. My name is Tomas Herrera, like all my co-authors, we are part of the Autodesk research in Autodesk. So here is a brief agenda of what we will be talking about for the next 10 minutes. We start with the intelligent construction rationale, or why are we doing this work. We present what we call the intelligent construction ontology. We describe a little bit about the agentic knowledge workflows we have that operate on top of the data, and we store in the intelligent construction knowledge graph. Then we show a small demo where we have a scaled down project of our construction data twin, and we show how the data we interact with the data, how can we derive insights or conclusions from that data. And then we finish with some conclusions and some potential next steps for the work. And before jumping into the content, I want to introduce the rest of the team because I want to put a face to the names that we have here. Basically, my colleagues Simon, Matthieu, and Mehrzad who are also present here. We're more than happy to answer any questions that we might have. You might have from the presentation either now or offline. And I would like to also invite you to a workshop that we're hosting in the next session right next to this one, where we'll be giving a little bit more information about the work that we are doing around construction data twins and how we collect the data. No? And with that in mind, then let's start talking about the reason why we're doing this, what we call the intelligent construction rationale. No? And it's basically like we have been talking about that for the last 3 days, about the construction projects are messy. So there is a lot of data, but the data is not interconnected. The data is owned by the different companies that act as stakeholders for the construction project, and there is no way that you can have a glimpse through all of that, and we know that because we are part of the Autodesk ecosystem. And we're talking about a lot of heterogeneous data, but it's like sitting in top of it's like having a pile of food but no cutlery in order to eat that food. So you don't have a way to gather to both that. So basically, you have a lot of project data, but that doesn't mean that you have project intelligence. So the data is there, but it's owned by the companies. They do what they do with that data. Sometimes they build some kind of tools to extract some analytics according to their own purposes, but there is no way to have a holistic view of the whole construction process. And that's what we try to come here. Now, so basically, I'm now thinking about the rising popularity of the digital twins. We think about building a construction digital twin for the construction process. And then now we have also the ontology, because some people even call the 2026 the year of the O, the year of the ontology, because to realize that LLMs or AI in general is not a magic wand that you can basically use. And hey, look at all this pile of data. Tell me what's going on here. That doesn't work. So we need to add some structure to that data. And that's the idea that we follow here. So basically, we have this what we call the intelligent construction approach, where we try to use ontological approaches in order to build the construction data. And to give you a little bit more of an idea of what's going on here, it's basically, this is a description of our intelligent construction approach. We have 3 main pillars. The first one is what the intelligent construction ontology that provides like a cross-domain linking. It's basically act as a connective tissue across all the different domains, all the different data points that we have. And then we have the agent-based workflow. We have a set of single-purpose, simple agents that they react to some event, they do their work, they operate on that data, and they go to sleep again. So basically, that's the idea. So you have one job, do it right. And that's the philosophy behind this single-purpose, simple agents. And then we have a knowledge graph to store all of this information. Basically, the knowledge graph doesn't copy the information, basically reference information, whatever it is. The knowledge graph is driven by ontologically driven by the intelligent construction ontology, and our contribution is we make causality as a first-class citizen, because we want to know whenever something happens that shouldn't be happening in the construction site, why this happened. It's always the question, why this happened? And then we have our data representation of the construction process, and we want to get insights from that. So basically, the idea of having causality as a first-class citizen allows us to go from the observations of the construction site to insights that are valuable for the stakeholders. And here is what we call the ITCO intelligent construction ontology. In order to not to reinvent the wheel, what we do is basically we import or we align with existing ontologies that give us all the concepts that we need in order to gather insight from the construction site. So when we talk about the BIM area, we leverage the BOT ontology that gives us access to building, storage space, and building elements. And in case of building elements, because we have a huge amount of building elements, then we leverage from the smart building, the IFC taxonomy, and that's where we connect that. Well, we do this because we are handling a lot of BIM data coming in IFC format, and it's basically it's very easy to have a one-to-one mapping between the IFC IFC concepts and IFC elements and the corresponding concepts to ontology. When it comes to project management, scheduling management, and so on, we import data for construction ontology that give us all the concepts related to work packages, activities, tasks, and so on. And then on the right side, you have what is all the concepts related to Autodesk Construction Cloud, or now called Autodesk Forma, that gives all the concepts related to issues, requests for information, size, roles, users, and so on. Everything which is related to the project management side of things. And we connect them in a semantically rich way. And we also add all these concepts of sensor, observation, evidence, and assertion. That's basically one of our main contributions to the intelligent construction ontology. And these are the ones that give us the ability to perform this kind of from observation to state assertion pipeline. So basically, a sensor is, think about a sensor as a camera, a thermometer, a humidity sensor, all these kind of devices that provide time-dependent data. And an observation is basically the artifacts generated by this sensor. So basically like 1D temperature data, video frames, images, and so on. Then the evidence is something that is basically like something that is going on in this, that you see that is happening in that data, that is not, it's like something that needs to be observed. Like you see a spike in the humidity, you see a drop in the temperature, you see a movement in the construction site in a Sunday afternoon, or these kind of things. Those are observations, but also those are areas that need to be, that are also captured in our data set. And there is a one-to-many relationship. The evidence might be using multiple observations to justify an evidence. And the same applies to the connection between the evidence and the state assertion. The state assertion is not okay, there is something going on here. And that might be related to, let's say, you have a temperature drop and a humidity spike in a room that should be enclosed, that shouldn't be happening, and then that might be associated to an issue. It's basically, there is a wrongly mounted window in this particular room, or there is a task that should be marked as complete that is now under review. And this is the kind of information that we store in the graph. And everything is data set. The most important thing here is that we put everything in at the data level, because all the tools are, basically all the agents are working data centric. And basically this is the part that we use in order to basically store all the information and help us understand why something happened that shouldn't be happening. Now, the second pillar is related to this agent-based workflow. Remember, I was talking about these small single-purpose agents that work event-driven. So here we have a small diagram of how our pipeline works. We have the data at the center in our knowledge graph, and we have a bunch of agents like the observation agent, the beam agent, the semantic linking agent, and so on. I'm already at 8 minutes, so I should hurry up a little bit. And my point is that basically we have a connection between the graph database and a Kafka as an event bus, and then we react to events. So basically we have a broker agent that is always listening to the Kafka bus, bus, and then according to the events generated by the data, then it triggers the corresponding agents to work on top of the data. So that's basically it. So you're waking up, you do the job, and you go to sleep again. And by doing this, then basically we ensure that our workflow is complete data centric and everything happens at the graph level. So we have agents connecting to the beam port, agents connected to the schedule, agents dealing with the observation coming from all the sensing devices, agent ensuring that the data stored in the graph is corresponds to the INTC ontology. All the things are happening basically in a parallel way and in an independent way. And then the third pillar is the knowledge graph. Basically, we have the ontology, and then we decided to go for Neo4j for storage solution. I want to go basically the reason why we went with Neo4j because of legacy reasons, and people also feel comfortable with that. The problem is that Neo4j is, so we have our ontology using alpha using Protege from an LDF approach. Now we have an RPG graph database that we're using. How do we handle this? So basically we leverage the Neo-semantics package from Neo4j. We're able to import the ontology as you can see here into the graph. And then what we do is, instead of labeling the nodes in our graph, we connect all the instance data as to an instance of relationships to the graph. So we have the T box or terminology and the A box or session box or the instance data at the same place, and we have them all of them connected. Now remember, I was talking about the semantic linking agent. That's the one that makes sure that all the connections are rightly set up. No? And by doing that, we avoid the over-leveling, and we have also access to the all of the ontological terms in LLPE relationship. And yeah, so I mentioned that we're using Protege to offer the ontology, and there you have here like this validation, small construction site that we built in one of our tech centers in Boston, where we built this small, it's a very small construction, 2 walls with all the framing, the HVAC connections, and the floor and the ceiling. And you can see on the right side basically how this looks like at the graph level, where the orange nodes are the classes of the concepts coming from the ontology, and the gray nodes are the instance data, all properly linked. And when you add the schedule information in order to build this, this is how the graph looks like. It goes way bigger, as you might see now. And then this is here how the graph looks like when we start this video. This is how the graph looks like when we have put all the construction data that was related to the construction of this small scaled down example in our construction site. And we have here observations, building elements, data sessions, and evidence. On the lower right, what you see is LMV, which is the dash model view from Autodesk, where we can load the big data, and then we can basically have access to all the images, all the coming from the sensor devices, to all the drawings, to all the information associated to the construction site. And based on that, then we can now go and look for the observations. So we're going to see all the observations and the related of the dependent information related to the observations for a given building element, which is this one. So we can then now filter down. We can click on an evidence, and we can see the relationship between evidence, observations, building elements, and state assertions. So we can see the state assertion here, and then we can experience. You can basically look at which are the observations that were that are said to this particular evidence and state assertion to this particular building element. This kind of the debugging tool that we build in order to prove our point, to see how all the data is connected together. And that's it. I mean, basically, to conclude my brief presentation, 12 minutes, which are our main contributions here in our paper. So we provide like a cross-domain ontology that provides a language for all this heterogeneous data that help us to basically to link data coming from different stakeholders, from different aspects, and also specifically to connect the accurate information coming from drawings, specifications, and requirements with the on-site observations, all the real-time data that is coming into the construction site. So we are basically building like an efficient progress tracking tool that where we can see how the actual view is the actual view of the construction site compared to what should be happening according to the schedule and on the requirements that we have. So we can confirm that we are time compliant and also requirements compliant when it comes to the connecting this as is with it should be. And also the idea of having the causality as a first-class citizen, bringing all this information related to observations, state assertions, and evidence also at the graph level, so that, let's say, if somebody joins the team and wants to look at what's going on here, all this information is already stored and provide context to all the decisions that were taken during the construction site. And looking forward, the next steps, basically, like you see, this is a scale down project. We want to try this, and we already have looking at how, so we already have working with the large construction companies, looking at larger construction sites and see how our approach will work there. We're also looking at tools in order to avoid the performance bottleneck, like sharding the knowledge graph according to space, systems, etc., or only adding the building element nodes as they are excited, because as they are needed. Because if you remember, an IFC file has a lot of elements. We don't need to put all of them a priori in the graph because it's going to explode the database. So we need to be careful on that. And then basically we are doing also a lot of work on this evidence-based causal analysis. So basically when something happens, why it happened, and eventually can we avoid this happening again? And with that, I'm going to stop now. I'm going to thank you for your attendance and happy to answer any questions.